Okay, and so last time we were working on the one-dimensional harmonic oscillator in the energy representation. Okay, and so the first part of that is you write down an operator called the lowering operator, which is m omega over 2 h bar times the position plus I times square root of 1 over 2 h bar m omega momentum, and its Hermitian conjugate. So you basically just change the I into minus I, because everything else is either real numbers or Hermitian operators. And the nice thing about doing this is it then turns out that the Hamiltonian is equal to h bar omega, a dagger a plus 1/2. And a and a dagger satisfy a very nice commutation relation that the commutator of a with a dagger is equal to just 1. Okay, and we also know, because there's a general theorem that tells us that this is true of bound states in one dimension, that there are unique energy eigenstates. They're non-degenerate. Okay, and we learned last time that we can label them by integers, where the integers n are non-negative. And the lowest one, the n equals 0 one, is the ground state. That's the one with lowest energy. And we also know that these are orthogonal. Why do we know that? We know that because they're eigenstates of the Hamiltonian, and the Hamiltonian is Hermitian. So because H is Hermitian, they are orthogonal. That's because they have different eigenvalues. If they could have been non-degenerate, then we would have had to worry that maybe we have to do Gram-Schmidt or something to make them orthogonal, but we don't have to do that. And so if they're orthogonal, that means we can choose the normalization of each of these kets so that they're orthonormal as well. So choose normalization so that if we take the inner product of one of these with another one, n with k, we get a Kronecker delta, delta nk. Okay, now, if n is an energy eigenstate, so if n is energy eigenstate, as we are assuming, then we proved last time that if you act many times with an a dagger operator, you still have an energy eigenstate. So then a dagger repeated k times to the kth power acting on n is also. And the energy eigenvalue of that state is energy equals h bar omega times n plus k plus 1/2. Every time you act with a dagger, it raises the energy. Okay, but we have to be careful because this is not going to be necessarily normalized to 1. So it's proportional to the state n plus k, but it's not equal to the state n plus k. So what we have to do now is we have to figure out how to normalize everything in order to make these things be orthonormal. And so to do that, let's let n be equal to some normalization factor that we have to figure out times a dagger acting on n minus 1. So here we're just doing this, but we're just choosing k equals 1 just to make things easy. And so the k sub n here is a normalization factor. We know they're proportional, so it's a normalization factor, and our job now is to find out what it is. Okay, and the tool we're going to use to find out what it is to demand that n be the states n be orthonormal. Okay, so if we have this equation, we can take the Hermitian conjugate of it. And so we know n Lebras is equal to k sub n star. K sub n is some number, times n minus 1 Lebras acting on the right by a. We changed a dagger into a. Okay, and so now we can compute the matrix element of n with n. Okay, on the one hand, we're going to require that this be equal to 1. On the other hand, we can use the fact that this is the magnitude of kn squared times n minus 1 a dagger, n minus 1. Now we can simplify this because we know a dagger is equal to a dagger a plus 1. So what we did there is we used the commutation relation to relabel or to reorder this. So this is a dagger a plus 1, and that's actually equal to the Hamiltonian divided by h bar omega plus 1/2. And the nice thing about that is we know what h is acting on the states n minus 1, so we can simplify things. This is equal to magnitude of kn squared times n minus 1 times h bar omega n minus 1 plus 1/2 over h bar omega plus 1/2, all acting on n minus 1. Okay, so we've just plugged in for this h, the number that it is equal to. Okay, and now this simplifies to nothing other than n. The whole thing, remember, is supposed to equal 1. Okay, and so this is equal to k sub n squared. I should put this in, oops. I should put this in absolute values, times n minus 1, n minus 1, which is 1, we're assuming. Okay, and so what we learn is that we can choose that our k sub n is equal to 1 over the square root of n. Now, whenever we find the normalization of an eigenstate, there's always a phase ambiguity. It never fails. And so because of this absolute value squared here, we could have put some phase factor that we wanted there, but there's just an arbitrary choice that we make. And so we're just going to choose it to be real and positive because why not? It makes things nicer. So I want to emphasize, though, this is a choice we're making. Then once we've made that choice, what we've learned is that the ket n is a dagger over the square root of n times n minus 1. Okay, or we can rewrite that just by multiplying through by square root of n and get a dagger acting on n minus 1 is the square root of n times n. Okay, or we can now relabel n as n plus 1. And the only reason for doing that is because now we get a dagger acting on n is square root of n plus 1 times n plus 1. Okay, so this is a recipe that's telling us how a dagger acts on any energy eigenstate. It gives us the next higher energy eigenstate, but for everything to be normalized, we need this square root factor. Okay, and similarly, if you do everything that I just did, but with a replacing a dagger, you get that a acting on n is square root of n acting on n minus 1. Okay, so these are very important equations because they tell us how to make a and a dagger, how they operate on energy eigenstates. Okay, so for example, suppose we take a dagger A acting on n. Okay, we know what a acting on n is, so we can rewrite this as a dagger square root of n times n minus 1. Okay, and then the number we can just pull out, and so this is a dagger acting on n minus 1. That again gives us a square root of n, so there's two of them, which is just equal to n times the original eigenstate. So we've managed to construct an operator here whose eigenvalues are equal to the integers n. Okay, and so that's called the number operator. Just as a bit of terminology, capital N is equal to a dagger A equals number operator. And it's just the thing it's measuring, because it's a Hermitian operator, is it's measuring the number of energy quanta. Okay, and so H is just equal to h bar omega times n plus 1/2. And we just proved that n acting on a ket little n gives you back the number little n times n. Okay, other things we can do using these nice equations here are we can compute basically any matrix element we want. So matrix element examples. Okay, for a simple one to start off with, if we did the matrix element of a dagger between two states n and k that are energy eigenstates, we just use how a dagger acts, and this becomes n square root of k plus 1, k plus 1. Or we can bring the number outside. Okay, and now orthonormality of the energy eigenstates tells us this is square root of k plus 1 times delta n k plus 1. For a slightly more complicated example, suppose we were to want the matrix element of the operator x cubed in between the third state above the ground state and the second state above the ground state for some reason. Right, so now what we can do is we can plug in for x what it is in terms of a and a dagger. That's the general strategy. And so there's, each one of them comes with a factor of h bar over 2m omega to the 1/2. So there's 3 of those. And then there's 3a plus a dagger squared, 2. Okay, and now, oops, cubed. This should be cubed. And now we just have to multiply this thing out. And when we multiply it out, the one thing to be careful of is to make sure that we keep the ordering correct. And so to do that, we'll write this as h bar over 2m omega to the 3/2. And then there's 3, and I'm just going to multiply the whole thing out. There's a cubed plus a squared a dagger plus a dagger a plus a dagger a squared plus a dagger squared plus a dagger a dagger plus a dagger squared a plus a dagger cubed, all acting on the state 2. So again, here we have to be careful with the order. So a squared a dagger, for example, is not the same thing as a dagger a. Okay, and now the point is that this long expression is mostly going to consist of things that can't possibly contribute. For example, I'm starting here with a state with 2 quanta. And then if I look at this term, I'm acting on a state that destroys 3 quanta. So the first 2 are going to reduce this to the ground state. And then the last of these 3 is going to act on it and give 0. And so that contribution is just 0. We can cross that out. Okay, on the other hand, we have, for example, some of these other ones are 0. For example, this one is a dagger cubed, and then acting on the 2 state, it's going to give a state with 5 quanta. And so 5 quanta overlap with 3 quanta on the left here is going to give 0. Okay, and so that one's gone. Oops. That one's gone. Okay, and this one is gone also, this one right here. How is that? That's because you have 2 quanta, you act and you make 3 quanta, you get a state with 3 quanta, but then you destroy 2 of them. That gives you 1 quanta, and the overlap with 3 is also 1. So this goes away. And similarly, anything with 2 A's and 1 A dagger just goes away. And so we're left with only 3 things that do contribute. Okay, and so this is now something that you do have to calculate, but it's relatively easy. Okay, and so let me just mention a systematic strategy, something that you could teach your computer program to do to evaluate these things. It goes by the name of normal ordering. In quantum field theory, normal ordering is a very useful thing because if you don't normal order, you sometimes get infinities that you have to take care of. So this is a systematic strategy. Okay, and so the idea is you take any string of A's and A daggers, like the one above. Actually, when I say string, this would be a string of A's and A daggers. This would be a different one. This would be a different one. Okay, and for each one of these, you use commutator of A with a dagger is equal to 1 to rewrite as sums of strings with all A daggers on the left and all A's on the right. Okay, and so to do that, you're using that A dagger. Anytime you see an A to the left of an A dagger, you can rewrite that as A dagger A plus 1. And so you just use that recursively. Then once you've got all A's on the right and all A daggers on the left, the A's on the right lower the quanta in the ket on the right, and the A daggers on the left will raise the, they'll also lower the number of quanta in the bra on the left. And so one gets this systematically. So normal ordering isn't necessarily the fastest way to calculate anything, but it's sort of very systematic in the sense that it will always work for you. All right. So this was, I haven't actually computed this. There's a little bit more arithmetic one has to do, but this is the general idea of how to compute this matrix element. We can contrast with what this would look like in the position representation, or the X representation. So let's just write it down. Again, I'm not going to complete the calculation. I'm just going to write down the outline of what it would look like. Okay, so basically now in the position representation, we're integrating over all X. We put in a complete set of states in X. That turns everything into wave functions in X. And so there's the wave function for the 3 state, which is m omega over pi h bar 2 to the 6th power, 3 factorial squared, all to the 1/4 power. Then there was a Hermite polynomial. The Hermite polynomial was of this quantity y, which turned out to be m omega over h bar times x. And then there was an exponential factor, which looked like this. Okay, then we have our operator x cubed, which turns into the number x cubed in the position representation. And then there's everything for the state 2, which looks similar, m omega over pi h bar 2 to the 4th power, 2 factorial squared. Second Hermite polynomial. And then finally, there's an exponential. Okay, so now in the position representation, that's the integral you'd have to do. And the key thing to notice about it, of course, is that it's a horrible mess. And so even though in principle you could calculate the matrix element this way, it would be a very bad idea. And so specifically on homework 6, problem 4, I ask for a bunch of matrix elements. You can compute them in the position representation if you want to, but I don't recommend it unless you're really angry at yourself and you want to punish yourself for some reason. The fastest way to do it is generally going to be to compute everything into A's and A daggers and use the energy representation rather than using the position representation, because nobody wants to do an integral like this with those Hermite polynomials stuck in there. It would be a nightmare. Okay, questions on that? All right. So even though we're generally not going to use the position representation for specific problems, it's a useful thing to do to see how the energy representation translates into position representation. So from the energy basis, ortho basis, I should say, n, to the position representation, which means we're writing things in terms of wave functions xn for the energy eigenstates. Okay, so to see how to do this, recall, for example, that A was this thing. Okay, and in the position representation, we know what P looks like. P is represented by minus I h bar times the derivative with respect to x. And the operator x is just represented by the number x. And so the operator A is going to be represented by 1 over square root of 2 y plus d by dy. So this is the representation in the x basis, or in the x representation. But I've written it in terms of y. Recall y is just proportional to x. Okay, and then in the x representation means that this is going to be acting on wave functions psi n of x, which is x psi n, or really, I guess we use the notation that we called this thing just n for short. Okay, so acting on wave functions of x, A is given by this differential operator where y is defined in terms of x, like that. Okay, and then similarly for a dagger is represented by 1 over square root of 2 y minus d by dy. Okay, and so now the fact that A acting on the ground state gives 0 becomes, in the position representation, that y plus d by dy acting on the wave function for the ground state equals 0. Okay, so where we're going with this is we're now going to show that we can solve this differential equation to find the wave function of the ground state, which is something we already knew from the position representation, but we're sort of getting it, in this case, from the energy orthobasis representation. Okay, so our job is to solve that differential equation. Okay, and so we have d by dy acting on the wave function of the ground state is equal to minus y times itself, which tells us that d psi 0 divided by psi 0 is equal to minus y d by dy. Okay, that on the left-hand side, we have a differential of the logarithm of psi 0. On the right-hand side, we have the differential of minus y squared over 2. Okay, and now we can integrate both sides to get the logarithm of the ground state wave function is minus y squared over 2 plus a constant of integration, which I'm going to cleverly call the logarithm of another constant. It's a constant, so it doesn't matter what I call it. Okay, so this is just a constant of integration. Okay, and now exponentiate both sides to get psi 0 of x is equal to that constant times e to the minus y squared over 2. Or finally, I can translate everything into x and say that psi 0 of x is equal to constant e to the minus m omega x squared over 2 h bar. And now I can figure out what the constant is by requiring it to be normalized. And that gives m omega over pi h bar to the 1/4 times the exponential. Okay, so notice that what happened is we still had to solve a differential equation, but this differential equation was much nicer than the one we solved in the working directly in the position representation. But at least it checks. Okay, now having gotten this one, we could, again, in the position representation, you can solve the differential equation for all the higher energy states, but it's easier to instead construct them as follows. We know that they're equal to a dagger to the nth power divided by the square root of n factorial acting on the ground state. Okay, that's using how we know how a dagger acts on each state recursively. Okay, and we also know from up here, we know how a dagger is represented in the position representation. Okay, and so what we've got is if we take the wave function, oops, I wrote that wrong. If we take the wave function for the nth energy eigenstate and we plug in what a dagger is, well, first of all, there's the 1 over square root of n factorial. And then a dagger is 1 over square root of 2 y minus d by dy to the nth power because there are n of them. Oops, the n should go on the outside. Okay, acting on the ground state wave function, which is m omega over pi h bar to the 1/4 times the exponential. I'm going to rewrite the exponential, I'm going to write it back in terms of y again because I have differentials with respect to y, so it's easier to act directly on y. Okay, and what we learned before from the position representation is this was the following: m omega over pi h bar 2 to the 2n, n factorial squared, all of that to the 1/4 power, times e to the minus y squared over 2 times the nth Hermite polynomial. Okay, so now we can compare the two things. And we notice that what that does is it gives us a formula for the nth Hermite polynomial. And so by comparing, we learn that the nth Hermite polynomial of y is just equal to e to the y squared over 2, y minus d by dy to the nth power, acting on e to the minus y squared over 2. Okay, all the m's and omegas and pi's and h bars and factors of square root of 2 and everything just work out nicely. And so we've got this formula for the Hermite polynomial. And you may recall that when we were doing the position representation a couple of lectures ago, I gave this formula and said we would derive it an easier way using the energy representation. And that's just what happened. Okay, so here I should say this is according to what we learned before, according to the differential equations method in position space. Okay, any questions on that? All right, so the next thing we want to talk about is we want to discuss how harmonic oscillators are realized in the classical limit. And so let's talk about a macroscopic harmonic oscillator, something that you would actually see in a lab. where you could measure it with your own eyes. And let's say you're in an undergraduate physics lab and you have a mass of 1/5 of a kilogram. I'm choosing the numbers here to be round numbers so that things work out. And let's say it's on one of those little oscillation tracks, and it's moving back and forth with an amplitude x0, which is 10 centimeters or 1/10 of a meter. And let's say you've got it moving along pretty good. So the angular frequency is 10 radians per second, which is the better part of 2 complete oscillations per second. So it's moving pretty fast, but I want to choose the numbers to be round numbers. Okay, so there's a cartoon of our mass oscillating back and forth. And so let's first of all work out classically what the energy is. Okay, so classically the energy is p squared over 2m plus 1/2 m omega squared x squared. And we know that it's going to be a constant. We are neglecting friction and gravity and all that stuff. And since it's a constant and we want to evaluate it, we can evaluate it when p equals 0 to find out what constant it is. Okay, and so this is equal to 1/2 m omega squared times the amplitude squared when p equals 0. And so to find out the constant, we can just plug in the numbers. 1/2 times 1/5 of a kilogram times 10 radians per second squared times the amplitude is 1/10 of a meter. And that conveniently works out to about 1/10 of a joule. So now, to understand what this means quantum mechanically, let's remember what the energy quanta are. The energy quanta are h bar omega. Okay, and omega, remember, has units of 1/seconds. H bar has units of joules times seconds. Okay, and this works out to be 1.05 times 10 to the minus 33 joules in these round numbers. And so if we were going to choose a state, a quantum state to represent it, it would be the state n with n being an extremely large integer, namely e over h bar omega, which is approximately 10 to the 32. That would be the large integer that would seem to describe this classical state. So this is a quantum mechanical state with the same energy. So when we graphed these energy eigenstates, the larger n was, the more wiggles this thing has. And so this has an unimaginably large number of wiggles. And so the question we can now ask is this state with very large n classical-like? And the answer is no. So is the energy eigenstate n equals 10 to the 32 classical-like? The answer is no. And so how do we know it's not classical-like? For one thing, we can compute the expectation value of x, which is, I'll just write it as proportional, because that's all that matters here. This is proportional to a plus a dagger in expectation value. But then the a dagger acts on n and makes it into an n plus 1, which gives 0 overlap with n. And the a acts on n and changes it into n minus 1, which again gives 0 overlap. And so this is just equal to 0. And the same way, the expectation value of the momentum is equal to 0. So the x position and momentum expectation values are not only constant, but they're just 0. Okay, but that's not at all what a classical harmonic oscillator in the lab looks like. A classical operator has x and p that change with time in a very noticeable way. I'll write x classical as a function of time equals x0 cosine omega t plus some original phase. And the momentum classically is m times the time derivative of that x classical. Oops. This should have been a time derivative. Okay, and so that works out to be minus x0 m omega times the sine of omega t plus phi 0. Okay, so that's what a classical state should look like. It should not have x and p both with expectation value 0. Oh, by the way, when I said constants here, it's constants because these are stationary states. And remember, the expectation values, they're eigenvalues of energy. And when you're in a stationary state, the expectation values of observables do not change. And these x and p are both observables. And so we computed them to be 0, but we know that if there's 0 to start with, they're going to remain 0 because they're stationary states. So one thing that tells us is that when we're looking for a classical, I left out the word state here. When we're looking for a classical-like state, we don't want stationary states, because if it were a stationary state, then these things would just be, the expectation values would just be 0. So we're looking for something that's not a stationary state if we want to describe something classically. Classical does not equal stationary state. In fact, in some ways, classical means sort of the opposite of a stationary state. Okay, so let's look for something that looks classical. We're going to look for states with expectation value of x in the state as close as possible to what we know the classical trajectory of our mass is, and p as close as possible to what we know its trajectory is. Okay, now there's no guarantee that we'll be able to get very close from what we know, but it turns out we will be able to get extremely close to a classical-like oscillation. So these are called coherent states. Coherent is here a synonym for quasi-classical. Of course, they can't be exactly classical, but they're as close as possible. And what we've showed is these will not be energy eigenstates. All right. Now, since I know the answer in advance, I'm just going to write down the answer, and then we will prove that the states that I'm going to write down are the coherent states that we're looking for. So I'm going to try states that I'm going to label alpha that are eigenstates of not position or momentum or the Hamiltonian, but the destruction operator or the lowering operator. Okay, so that has some consequences, that choice. First of all, the lowering operator is not Hermitian. And it doesn't commute with the Hamiltonian, which is a sign that we might be on the right track, because if it did commute with the Hamiltonian, then we could choose these states to be energy eigenstates also, and we know we don't want that. So that's a good sign. The fact that it's not Hermitian means when we write down the eigenvalue problem, A on alpha is equal to the number alpha times alpha. The eigenvalue can be complex. There's no reason why it can't be, since A is not a Hermitian operator. And in fact, it will be complex. I can cross that out and write will be. Okay, and because, again, because this is not a Hermitian operator, the set of states alpha won't be an orthonormal basis. There's no reason to expect it would be, and so it will turn out it won't be. Nevertheless, these will be the coherent states that we're looking for. Okay, so having guessed that these are the states we want, we have to solve this eigenvalue problem simultaneously for the number alpha and for the ket alpha. And so to do that, we're just going to try the most general thing it could possibly be. We're going to write alpha as a sum over all the energy eigenstates. So we're working in the energy basis with arbitrary coefficients, C sub n, times the basis elements. Because the energy eigenstates are a basis, we know for sure that we can write it this way. And now we're going to write down the eigenvalue problem. A acting on alpha is equal to sum n equals 0 to infinity. Of course, these C sub n's are just numbers. So this is A acting on n. But we know how A acts on n. We worked that out before. So this is C sub n times square root of n times the state n minus 1. Okay, and now we're going to do a trick where we're going to relabel n as n plus 1. Okay, and so this is sum n plus n equals 0 to infinity. Cn plus 1 square root of n plus 1 times n. Okay, and you could worry about what about this extra term that I've added in, which is n equals 0, and the answer is, or sorry, n equals -1, which it turns out doesn't exist. So that's why I was able to sneakily change this n equals 0 to this n equals 0. Okay, and so now I can rewrite this, I can rewrite the left-hand side as also sum n equals 0 to infinity, Cn, the number alpha acting on alpha, right? That's because we're solving the eigenvalue problem here. Okay, so now we compare this expression to that expression. And what we learn is that Cn plus 1 has to equal the number alpha over square root of n plus 1 times C sub n. And so now we can solve this recursively. If we start with C0, then we can work out what all the other C's are. So C1 is equal to alpha over the square root of 1 times C0. And then C2 is alpha squared over the square root of 2 times 1 times C0. Okay, and C3 is equal to alpha cubed. We multiply by an alpha every time from here. And we multiply by 1 over square root of the next integer there. And so this is alpha cubed over square root of 3 times 2 times 1. Okay, or once you recognize the pattern, you see that the general coefficient C sub n is equal to the number alpha to the nth power over square root of n factorial times C sub 0. Okay, so what have we found? And then we'll exploit this next time. Up to normalization, which we will work out next time, the eigenstates of the lowering operator, which we're calling alpha, are equal to some overall constant C0 that we have to work out, times an infinite sum, n equals 0 to infinity, alpha to the nth power over square root of n factorial, all acting on the state n. Okay? So next time, what we want to do, we really have two tasks for next time. We want to find C0. That's just a question of normalization. And show that these states are classical-like. In other words, that their expectation values are not just 0 and not just constant, but oscillate just like a real harmonic oscillator that we know in the real world, that we observe in the real world. All right, so that's it for today. Looks like I went a little over, sorry about that. And I'll ask if there are any questions.
Thank you, Professor. I do have a question. It's a linear algebra question. It's
Okay.
a little bit primitive. If anyone else has questions, I'll let them ask first.
Okay.
Yes. I'm sorry. So when we have a degenerate, and this is somewhat relative to the midterm, like when we have a degenerate eigenvalue, we don't find the eigenvectors using that traditional method where we have the operator A times the matrix X, like potential eigencat X equals to lambda times that eigencat X. We don't use that method when we have degenerate eigenvalues?
Sure you can. Yeah. So you have some matrix A acting on some vector, let's say, equals, let's call it alpha for the eigenvalue. Okay, and that gives you a set of equations that you can solve, and the general solution will be the eigenvectors and the eigenvalues.
Okay, so I don't know why, what I did wrong, I was going to email you, but I said, well, while you're here, I might as well ask you. I thought like maybe for eigenvalue, I'm sorry, a degenerate eigenvalue, there might be a different approach. So we use the same approach, correct?
Use the same approach, sure. Now, what's going to happen is because they're degenerate, you're going to find that you have a family of solutions rather than just a single solution. Okay? And so then you might have to choose them to be orthonormal. To make an orthonormal basis, you have to maybe choose the right linear combinations, which Graham-Schmidt will do for you. A lot of times in practical problems, for example, on the one on the midterm, it's sort of not too hard to just see from the process of writing it down how to choose them to be orthonormal. But if you don't see it right away, or if you just get unlucky in your guess, you can always use Graham-Schmidt to make them orthonormal.
So, yeah, I couldn't figure out what I went wrong in the midterm question. Should I email you, or would you have time to explain, go over my mistake, or I don't know where I went wrong in that one.
Um, yeah, maybe we should turn off the recording here since
Yeah.
this is a specialized problem.